Hello engineers, welcome back. In the previous video we solved a lead code question, that is find if path exists in graph. So we have a graph with edges, and in this graph we needed to check if there was a path between 0 and 2. And to solve this we have used breadth first traversal or breadth first search, right? And as we know, it took a time complexity of v plus e. So this is the typical breadth first search traversal, right? Now can we do better? So there is a method in which if we represent the graph differently, we can achieve the same thing in O of one time, in constant time. And that is very efficient when it comes to solving problems related to connectivity. Let's say we have a graph here, Tom, Sam, Jerry and Harry, and we have Ben, Charlie and Stuart as another component in the same graph, but they are not connected. As you can see, there is a gap in between and they are not connected. Now the question I'm asking is, are Sam and Charlie friends? Right? And as you can see, there is a gap in between, and Sam's component does not have a link to Charlie. So we can visually tell that there is no relationship between Sam and Charlie, or Sam and Charlie are not friends, right? So this is exactly the same question as this one. Is there a path between two vertices in the graph, right? So let's see how we did it before. We use the concept of adjacency list. So we represented the same graph in an adjacency list like this. This is how we would do it. And then if we need to answer this question, are Sam and Charlie friends? So first we would go to Sam's vertex, and then we will explore all the vertices of Sam. And then from there we go to individual vertices, we go to Tom, and then we go to Jerry. And then once we finish the exploration, we conclude that there are no edges between Sam and Charlie. So we can say that Sam and Charlie are not friends. But for this, we have to use breadth first search or depth first search, and the time complexity would be O of v plus e, right? But there is a different way in which we can achieve this in constant time. So that is what we are going to discuss in this video. It is called disjoint sets, right? So the same graph, if we represent it in a different way, we can achieve this answer in constant time. Let's see how we can do that. So this is how disjoint sets work. So we have the edges here, the same edges that we have from the graph. For example, there is an edge between Sam and Tom. There is an edge between Sam and Jerry. There is an edge between Jerry and Harry. And these are the other edges, Ben and Stuart and Ben and Charlie. So there are 5 edges. Now instead of representing them in an adjacency list, I will represent them in an array, right? So this is how it goes. So to build a disjoint set data structure, we will need two things. First is the parent array and second is the size array. Okay. And as of now, all the vertices are in the open space. They are all individual elements not connected to any other, right? So this is the current state. This is the starting position of the array, right? Let's see the array a little bit. So first we have the parent array. And in the parent array, there are 7 nodes: Sam, Tom, Jerry, Harry, Ben, Stuart, Charlie. Okay, and the array's values are the same as the index, which means that Sam is the parent of itself, Tom is a parent of itself, and so on. So they are the parent of themselves. That's why they are individual elements. They are not connected to anybody. And there is another array called size array, which is also having 7 elements, and currently all the sizes are 1. So if you look at it from Sam's point of view, there is only one node in this, one vertex in this, and that's why the size is 1, and so on for the rest of them, right? So this is the start position. Now what do? We take one edge and then we do these two things. We do find and we do union. Okay, now let's see step by step how we will achieve this. First, let's say we have the edge Sam and Tom, right? Now first thing we need to do is find who is the parent of Sam and then find who is the parent of Tom. Okay, for this we will use the find operation. Find operation will return the root. Okay, root means parent of itself, right? So let's see. So for Sam and Tom, who are the roots? For Sam, the root parent is 0. For Tom, the parent is 1, right? So the parent of Sam is 0, the parent of Tom is 1. If they are different parents, then we will perform union. Okay, so what does this mean? Currently we have Sam, we have Tom, and their parents are themselves. There is nobody above them, right? Their parents are themselves. But this one, this edge indicates that there is some relation between Sam and Tom. Okay, and that is not currently captured in the array. That is what we will capture now. So how will we capture that? We will capture that using the concept of union. Okay, so what does union do? Union says smaller size goes to bigger size. Now let's see. Now we have Sam and Tom. Let's see the size of Sam and Tom. Currently the size of Sam and Tom is the same. When it is the same, it does not matter who goes to who. It does not matter who becomes the new parent of who. Okay, so let's make Sam as the parent of Tom. Like this. Now Tom's parent is Sam, which is 0. Okay. Now since Sam is the parent of Tom, we will make a connection like this. Visually we can see it like this. Okay. We are just using the array internally, but visually to understand, I'm just showing you the connection. Now we have made a connection between Sam and Tom. And now we can see that Tom has a parent called Sam. Okay. And one more thing, because now Sam's size is 2. Sam is now having 2 components. We will update the size of Sam. Okay, so this is how the algorithm works. Now we will repeat the same thing for the rest of them. Now let's take Sam and Jerry. So who are the parents? Who is the parent of Sam? 0 itself. Who is the parent of Jerry? 2 itself. So 0, 2. Both are different parents. So we perform a union, and union by size. Okay, smaller size goes to bigger size. Let's compare. Sam and Jerry. Size of Sam is 2. Size of Jerry is 1. So Sam has a bigger size. So Jerry will have a new parent called Sam. Jerry goes to Sam. So let's make the connection. First, Jerry's parent is updated. Now Jerry also has 0. Next, we will make the connection to visually see that Jerry now has a parent, and this component now has 3 things. So size is also updated. Size is 3 now. Okay, so we are done with this. Let's continue. Jerry and Harry. So who is the parent of Jerry? Sam. Who is the parent of Harry? Itself. So there are different parents. So we perform a union. So let's make it union by size. So again we compare the sizes. The size of Jerry is 1. The size of Harry is also 1. So no problem. So Jerry can become a parent of Harry. Let's do that. So Harry now has Jerry as the parent. Let's make the connection. And Jerry's size is now 2. Okay, let's move on. We have Ben and Stuart. So who is the parent of Ben? Itself. Who is the parent of Stuart? Itself. There are different parents. So we make a union. So how do we make a union? We do it by size. So let's check what is the size of Ben? 1. What is the size of Stuart? 1. So no problem. Anybody can become the parent of anybody. So let's make Ben the parent of Stuart. So Stuart will have a new parent called Ben. And let's make the connection. And now Ben's size is 2. Finished. Now let's look at the last edge. Ben and Charlie. Who is the parent of Ben? Itself. Who is the parent of Charlie? Itself. So there are different parents. So we make a union. Union by size. So let's compare. Ben is having size of 2. Charlie is having size of 1. So Ben is greater. So Charlie will go to Ben. So Charlie will get a new parent called Ben. And we'll make the connection. and now Ben's size is now 3. And that's it. So now we have created a parent array which is representing the exact same graph that we had before. This is the exact same graph, but now we have represented them in an array instead of an adjacency list like this, right? So we have kind of reduced it to one dimension. Now let's try to answer the question. Are Sam and Charlie friends? So for this, we will ask who is the parent of Sam and who is the parent of Charlie. If they are having the same parent, which means they belong to the same component and they are friends. If they have different parents, it means that they are not friends. So let's ask. Sam and Charlie. Who is the parent of Sam? Itself. Who is the parent of Charlie? Charlie is having a parent of 4. But 4 is not itself, right? So you can see here return root. Okay, so whenever we are asking for find method, it will return the root. So who is the root of Charlie? Ben. And who is the root of Ben? Ben itself. So we have found our root. So Sam is having 0, Ben is having 4. So they are different parents. That's why they are not friends. So we can answer that in constant time. But you can say it is not really constant time, because first we are going here and then we are going to Ben to check whether it is the root, right? So it is not exactly constant time. So what we will do is we will implement a concept called path compression. So let me tell you again what happened. So when we are asking for parent of Sam and Charlie, so what are we saying? Who is the parent of Sam? It is 0. So because it is the parent of itself, we found the root. So there is no other element above Sam. So we have found our root. But for Charlie, the parent of Charlie is not itself. So we need to go to Ben first and then check for Ben, is there any other parent, right? So imagine if Charlie had more things like this. And we were asking, let's say, who is the parent of B? First we would go to Charlie and then we will go to Ben and then we will check if Ben is the parent of itself. So it is not exactly a constant time operation, right? That is why we will do a path compression. So what does path compression means, right? So when we are doing a find operation, let's say we are doing a find operation of B and we find that the parent of B is not B. So we go one step higher. So who is the parent of C? Parent of C is not C. Parent of Charlie is not Charlie, it is Ben, right? And then we go one step higher. So who is the parent of Ben? Parent of Ben is Ben. Yes. So this is what is returned as the answer. So this is Ben. So Ben is the root of B. So this is the answer for who is the parent of B, right? But to do this, we need to do recursion multiple times. And the tree can be longer, so it is not exactly a constant time operation. But we need it to be constant time operation. That's why we do path compression. So what do we do? In this recursion process, whenever we find that the parent of current node is not itself, we will go deeper into the tree. Once we find the root node, we will pass it down. Okay, I found the root. It is Ben. So whoever is in this path, in this recursion path, will carry a new parent now. Instead of whatever is the current parent, we will use the root. And root is passed down to the depth of the tree. So in this way, we will keep updating the root. Now this fellow will also have Ben as the root. So that next time when we ask the question, who is the parent of B, we will immediately get the answer as Ben. That will be in constant time. So what do we do now? After building the whole array, right? First time when we are asking, are Sam and Charlie friends? First we check who is the parent of Sam. This is root itself, so no problem. But for Charlie, this is not the same element as itself. 6 is not equal to 4. So first we have to go to 4 and then we have to check the root, right? First time. But when we are doing this process, let's update it. Because these edges are not changing, right? So we can directly update it saying parent of Charlie is 4, right? Parent of Charlie is 4. Now this is becoming a two-step operation. First I go to Charlie, then I go to Ben, and then I found my answer in constant time. So because this is Ben, maybe it is not clear. So let me introduce a new edge like this. Then it will be more clear. What is path compression? Let's say we have a new edge between Sam and Ben. Now let's see. So we do the same process. Find the parent of Sam, 0. Find parent of Ben, 4. There are different parents, so we perform a union. So union by size. So what is the size of Sam? 3. What is the size of Ben? 3. So no problem. So let's connect Ben with Sam. Now Ben will have a new parent called 0. And the size of Sam will be updated. Now we are getting 3 more nodes. So size of Sam will be 6. Right? So this is the updated array. Now let's also visually do the connection. This is the new edge. Now let's ask the question again. Are Sam and Charlie friends? Now let's see. What is the parent of Sam? 0, no problem. But what is the parent of Charlie? Charlie has 4. Who is the parent of 4? 0. Who is the parent of 0? 0. So it is taking multiple steps, just like this example. Who is the parent of B? Charlie. Who is the parent of Charlie? Ben. Who is the parent of Sam? See, now it is taking 3 steps. So in order to avoid this, we will update it. When we do the find method again, we will simply update it. Once we find our answer that, hey, Charlie now has a new root. It is no longer Ben, but there is a new root above Ben, which is Sam. So we will update it to 0. So next time if somebody asks the same question, are Sam and Charlie friends? We will say, Sam's parent is 0, Charlie's parent is 0. Yes, they are friends. And you can see it visually as well. Now we have a connection. Right? That's how path compression works. So quick recap, what is path compression? When we are doing find algorithm, if we find a node that does not have a root of itself, we will simply update the parent with the current root so that next time when we ask the question, it can be answered in constant time. Next time it is a simple lookup, right? Charlie is having 0. Who is the parent of 0? 0. It is a two-step comparison, which is same as constant time. Instead of going 1, 2, 3, 4 steps, right? And you can imagine if the tree is longer, that would take more steps. So that is the concept of path compression. Okay, so this is the theory behind disjoint sets. So I hope you have understood the concept of disjoint sets. In the next video, we will code all this in C++ so that it is even more clear for you, right? So that is it for this video, guys. I hope you found this helpful. I hope the visuals have made it intuitive and clear for you. If you have any questions, definitely ask me. In the next video, we will code all this and see how it works, right? Thank you so much for watching. If you have any questions, definitely leave a comment and ask me. And don't forget to leave a like if you found this helpful. Do consider subscribing if you haven't done already. And do bookmark the playlist and share it with your friends. Thank you so much for watching. I will see you in the next one. Cheers.